In this video, we'll talk about two more types of solution forms that can come out of solving a linear system of equations, and then see how they appear in the matrix and row echelon form of this process. Here we have two examples of linear equations. We have the first set, x1 plus 2x2 is 5, and 2x1 plus 4x2 is 3. And the second set, x1 plus 3x2 is 4, and 2x1 plus 6x2 is 8. Now, we can go about trying to solve these equations just by elimination methods. But if I double the first equation in both cases, and then subtract them, I can see what happens here. Well, for the first one, I will get 2x1 plus 4x2 plus 10 minus 2x1 plus 4x2 equals 3, which means when I do the subtraction here, I'm going to get here 0 equals 7, and that's just false, right? That's never true. So this tells me that this first set here has no solution because I get an equation out of it that is never true. For the second, if I follow the exact same approach, double this and subtract them, I'll end up getting 0 equals 0. Which doesn't necessarily mean that it's true for all x1, x2, but it means that I sort of get down to one equation here that doesn't really affect things, and I can just focus on one of the two equations before, tell me what's going to happen. So for this, we can see that in the first case, there's no solution, while in the second, I get 0 equals 0, which means really these two equations are the same. And we can also see that directly by looking at them, right? The second one is just twice the first one, and every single term it is doubled. So they're really the same equation, and I really only have one equation here. So the one equation gives us all of our possible solutions, in that if I pick anything for x2, picking x1 equal to 4 minus 3x2 will give a pair of points that solve the equation. So for any x2, or it could also be written as in vector form, x1, x2 equals t for being the any value you pick for x2, and then 4 minus 3t in the x1 component. So we have our results where we get one solution. That was pretty straightforward to figure out. And we have these two where we get no solutions out of this first one because the equations are inconsistent, and an infinite number of solutions out of the second one where we sort of have a redundant equation. So in the first case, we have an inconsistent system, and in the second, we have a redundant equation giving a non-unique solution where I have an infinite number of solutions for that system. The next thing we want to ask is it possible to determine this, what kind of solution we're going to get, just from the row echelon form, reduced row echelon form, or the matrix approach to this problem? And the answer, thankfully, is yes. Let's look at these two examples in this way and see what we get. So the first example would look something like 1, 2, 5, 2, 4, 3. This is the augmented matrix from the system x1 plus 2x2 is 5, and 2x1 plus 4x2 equals 3. Our first situation above. We can now take this to row echelon form. I already have 1 in the top left corner, so I can subtract 2 times row 1 from row 2. Row 2 should be row 2 minus 2 row 1. That will give me 1, 2, 5, 0, 0, 7. Where now this last equation has now become our 0 equals 7 that we got before. And this here, having this zeros equaling 7, tells us this is inconsistent because that gives rise to the equation 0 equals 7. To compare this, let's see what happens to the other situation. The other system we had in matrix form was 1, 3, 4, 2, 6, 8 in augmented matrix form. I can again go to row echelon form by doing the same operation to get 1, 3, 4, 0, 0, 0. And in this case, this row of zeros is our 0 equals 0 equation. So that is our redundancy or our non-unique solution. So how do we talk about these and what's actually going on here? The issue, and when one of these comes about, is the fact that I have a 0 row at least on the left side of my augmented matrix. So when we get a 0 row on that side in the row echelon form, then we have two options. If the right side entry is non-zero, then it would in some sense become our pivot column in the row echelon form. Then we have an inconsistent system of equations, which means there is no solution. The other option is if the right-hand side is 0. Well, in that case, this entire row is all zeros, which means one of the equations was redundant, which is likely to lead to non-unique solutions, assuming we started with the same number of variables and equations. And how can we write out these non-unique solutions? We'll want to look for columns in this augmented matrix which correspond to variables that are non-pivot columns. So let me write out that row echelon form from before. We had 1, 3, 4, and then 0, 0, 0. So this here is a pivot 1. It's the one at the front of a row of the matrix. So that's what column I want to use. But this column here has no pivot 1s in it. It's more impactful to see this if you're looking at a larger system where you'll have one column that doesn't have any pivot 1s in it at all. But in this case, that does not have any pivots. It has none of these leading ones. This is a non-pivot column that corresponds to a variable. And so what I can do is I can then use that variable as a free variable to determine my non-unique solutions. So use the non-pivot column variables as free variables. So for example, I will use t for that. So we're going to set x2 to be t, and then I'm going to use this equation that I have up top when I go to solve this out. I'll use this to write x1 in terms of t. So I have x1 plus 3t equals 4, or x1 equals 4 minus 3t, and that's the solution that we found previously. The important thing to look out for in these systems in the row echelon form version is, do you have any 0 rows, specifically on the left side of your dividing line? If you do, you're likely either in the case of an inconsistent system, if this right-hand side entry that pairs with that 0 row is non-zero, that's inconsistent, or if it's all 0, you likely have an infinite set of solutions that you can get by looking at the non-pivot columns, use that as your sort of free variable, and use that to determine what your solutions would look like for these types of system equations.